Hi, Mark Schuyler. Today we're going to look at a small but important lesson about the difference of two perfect squares. And you can see here in my picture that I have a larger square, a by a, and I'm subtracting from it a smaller square, b by b, and that's why they call this the difference of two perfect squares. You know that difference means subtraction, and that's what's going on here. I'll just write up the title, The Difference of Two Perfect Squares. So, how do we handle the most challenging SAT problems and ACT problems that involve this bit of algebra? It is algebra that you're supposed to recognize. You're supposed to recognize this expression right here. When you see this, you're supposed to have a little strike of lightning in your brain. It's supposed to be, oh, that's important. And what it factors out to is right over here. It factors out to the quantity a plus b times the quantity a minus b. The difference of two perfect squares, we'll see in a little bit, is actually one of three classic factorables that you need to know if you're going to maximize your score. So let's move ahead to the next slide. I've got a slide ready for you here with a really typical SAT problem. Let me read it aloud. If a squared minus b squared, aha, there's that strike of lightning, equals 15, and the quantity a plus b equals 5, then what's the value of a minus b? Well, again, the important thing is to recognize this and instantly factor it. So I'm going to do that down here. I know that a squared minus b squared equals the quantity a plus b times the quantity a minus b, but this is what I'm also catching. I'm catching the opportunity to substitute in the number 5 for a plus b down here. Now the reason that's so important is we're told that a squared minus b squared is equal to 15. So let me put that in. So right now, if I do my substitution, 5 is equal to the quantity, I'll draw a little arrow, a plus b, then 5 times something, 5 times some other quantity, is supposed to equal 15. Well, I think everybody knows that 5 times 3 is equal to 15, which means the entire quantity, a minus b, equals 3. And that's what they were looking for. Look at what the punchline to the question is. They want the value of the quantity a minus b, and we have it. It's 3. Now, what I really like about this problem is nowhere did we have to find the exact value of a. I don't know what a is. Nowhere do we need to find the exact value of b. I have no idea what b is. I just know that when you subtract the one from the other, it equals 3. So this is a real time saver. I think many of my students, when they're confronted with this problem on the standardized tests for college admission, what they do is they think they need to go about the very long, more complicated route of solving for the individual values of those variables, but you don't need to. I've got another slide here for us to practice on. Let's take a quick look at this one. Again, I recognize the difference of two perfect squares. I know I need to factor that and set it equal to 56. Notice I'm using x and y now instead of a and b. So I know that that's going to be the quantity x plus y times the quantity x minus y equals 56. Here is my substitution opportunity. I'm pretty sure you can see to drop in 8 down there, always looking for substitution opportunities. So let me just write it out. I think you can already figure out 8 times what is 56, but let me drop in, substitute the 8. And we know we could divide both sides by 8, and that would leave us, after these guys cancel, with the quantity x plus y must be equal to 7. There it is, and that's what they wanted. That's all they wanted. Once again, I don't know the individual values of x and y. Don't need to know. If the problem did ask you for the value of x, not just what x plus y is, it's actually pretty easy to solve. You would just create a system. Let me explain. You already know from the problem that they're saying that, let me change colors here. I think it'll make it stand out. You could already write down what they told you. They told you that x minus y is equal to 8. You discovered on your own that x plus y is equal to 7. So if they were asking for the value of x, treat it like a system. You could line them up, and you could try to do what's sometimes called the elimination method. You're hoping to either add or subtract in such a way that one of the variables goes away. And indeed, how convenient. The y's go away, leaving us with 2 x's on this side of the equal sign and 15, a total of 15 on the other side of the equal sign. So a single x is 7.5. But in many of the problems, you don't need to solve by using a system of equations. You just know that the whole quantity, x plus y, is equal to 7. So I hope this is making sense. Let's take a quick look at another slide I've readied for you. Here we go. This is the really important one. It's the one we've been practicing. Once again, it's called the difference of two perfect squares. But there are 2 other classic factorable expressions. I alluded to these in the very beginning of the video. Here's one. It's a squared, but look, there's a middle term here. We don't have any middle terms in the equation above, but here we do. A squared plus 2ab plus b squared equals a plus b times a plus b. The quantity is a plus b times a. So that could be written, obviously, as the quantity a plus b squared. We have a very similar looking equation immediately below. The only difference is this negative sign. Other than that, these 2 equations are the same, but look what happens when you factor it. You get 2 quantities that have different signs. Now these are a minus b times a minus b. Obviously, we can write that as the quantity a minus b squared. So there they are. 1, 2, 3 classic factorable expressions. Anybody who's spent enough time in algebra where they feel that they should be getting a pretty good score on the SAT or ACT, these are 3 expressions you don't want to be rusty on. They do show up on every test. Let's take a look at my last slide. What I've put together here is a challenge problem. This is where I've combined 2 different of the classic factorable expressions into one problem. So let's not worry about how hard the challenge problem is. Let's just worry if we know the 3 classic factorables. And sure enough, here we go. The most important one, the difference of 2 perfect squares, is equal to 35. So let's write that out. We know we should instantly factor it. When given that, we factor it, make our lives a lot easier. Okay, and that's equal to 35. Oh, here's our substitution opportunity. The quantity x plus y is 5. So 5 times what is 35? Well, I know you know, it's 7. So that's great. We know, and I'll write it over here, that x minus y equals 7. The problem told us that x plus y is 5. Now we could figure out the exact values of x and y by performing a system right now, but we really don't need to do that. That would slow us down, and we want to have time on these tests. So here's where the time saver is. I noticed that this bit of algebra that they're asking me about here is another one of the classic factorables. So I recognize that this one is actually the quantity x minus y times the quantity x minus y times itself. It's x minus y squared, the whole quantity x minus y squared. Well, we have it here that x minus y is 7. So 7 times 7 is 49. We've gotten the answer to the challenge problem right without actually taking the time to solve for the individual values of x and y. We just treated it as bits of algebra where whole quantities stand for something, and we can substitute them in and solve for them as a quantity. I hope you found that short little 10.5-minute video helpful, and keep your eyes peeled for the difference of two perfect squares and the two other factorable algebraic expressions.